Hello, I would like to welcome you to lecture 7 of 3N03. We'll start in this lecture to discuss the PN junction, how it operates, and the concept of a depletion region, potential barriers, and so on. And I will show you how this device is very useful, especially in the area of rectification, how to rectify an AC signal into a DC signal. The material that we'll cover today is from section 1.5 of our textbook and section 2.1. So these are the two sections from the book of Floyd. I would also mention that there is an application at the end of chapter 1. I strongly encourage you to read that application. Very interesting about how solar cells work, because solar cells are nothing but PN junctions. So we'll try to cover today what is the theory behind the PN junction, its structure, depletion region, the bias conditions. We may be able to touch on the IV characteristics as well. So in previous lectures we explained that there are an N-type material like this one shown here, where the majority of the carriers are electrons. Here you have pentavalent impurities. Each one of these impurities supply one electron, and these electrons are are available for charge. They have enough energy to conduct. So this is an N-type region. In the P-type region, we have mainly holes because we created the trivalent impurities. We introduce them into the silicon or the other semiconductor material, and there are holes, and these holes are ready to be filled by electrons. So here we have majority carrier electrons, very little holes as shown here. Here we have majority carriers holes, very little electrons. So what will happen when you put a piece of N-type material and a piece of P-type material in touch together? What will happen is that there is a physical operation or a physical phenomenon called diffusion. It is the same process that happens when you spray some perfume and this perfume starts to spread, the smell starts to spread. Because what's happening, the molecules of these perfumes, they collide together and they start to spread over a larger volume. This is called the process of diffusion. And this diffusion is really governed by some mathematical equations. There is something called diffusion equation. And use them in many disciplines. So this is what's going to be happening here exactly when you put the N-type material in contact with the P-type material. These electrons will start to diffuse from the N-type to the B-type. And when they diffuse, remember, this side was electrically neutral. Every atom was electrically neutral. When every electron here leaves its impurity atom and across to the other side, it leaves behind a positive ion. It leaves behind a positive ion. And when it crosses to the B-type material, it recombines with a hole. And then, and because of the hole also, the atom or the impurity atom of the hole was also electrically neutral. When the electron moves there, it creates a negative ion. So what's happening is that the electron will leave behind a positive ion on the side of the N-type material, and then because it moves from here to here, it creates here a negative ion on the B-type material. And this will start to create what we call a BN, a depletion region. This is a phenomenon of a depletion region, as I will show you in a second. So this is simply a process of diffusion. Electrons very close to the edge, very close to the contact, will diffuse, leaving behind them positive ions and creating on the other side negative ions. And by the way, this process happens in a fraction of a microsecond. It happens in a very short time. So this is the case after these few microseconds or fraction of microseconds will allow it to pass. Some electrons already diffused from here to here. When they left behind them their atoms, they left here on this side positive ions, and you should understand why they left behind positive ions, because every impurity atom was electrically neutral. So when it loses its electron, becomes a positive ion. And this electron jumped to the other side, it recombined with a hole, it filled the hole, and then because it was introduced to another impurity atom, it created a negative ion. Now, and what is the consequence of this? Now, I explained to you earlier that if you have electric field always points from positive charges to negative charges. We talked about that when we talked about charges. And this electric field, if you have an electron, it will try to move the electron in its opposite to its direction. So now what is happening is that this very strong electric field, which is pointing from the positive ions and negative ions, is really trying to stop the flow of any further electrons into the p-type region. It creates a barrier. And this is very well known phenomenon in physics, that when you have a reaction, it creates a counter reaction trying to stop it. So the diffusion was a process, and the diffusion resulted in the creation of this depletion region. But this depletion region created a very strong electric field pointing from the positive ions to the negative ions. This electric field is trying to push electrons on the other side. It's trying to push it from left to right. It's trying to stop it from diffusing further into the B region material. And you reach a state of equilibrium where we have here a depletion region. We call it a depletion region because it does not have free charge, it has only ions, and has very strong electric field. And as we agreed, when you have a strong electric field and you have a distance like this one, this is what we call a voltage difference. And this voltage difference, really, if you measure it, it's an intrinsic. It's the voltage difference across the depletion region. It's usually about 0.7 volts. It's 0.7 volt. Okay, so this is really the basics of this one. So when you put the N-type and B-type material together, they create a depletion region. This depletion region has very strong electric field. It's trying to stop electrons from further diffusing into the B-type region, and then it stops the diffusion. So this is how this process is created. This is one way of looking at it physically. Now we move to think about how this process can be interpreted in terms of energy bands. We agreed that in the N-type material, the majority carriers are electrons, and they are in the conduction band because they all have enough energy to be free electrons. While in the B-type material, most of the carriers are really holes, and they are attached to their electrons, so they are in the valence band. And when you put these two together before the formation of any depletion region, what will happen is you can see there is an overlap between the conduction bands in both regions, meaning that an electron that has sufficient energy on the N-type material can cross to the B-type material. It can create a current. So it can cross to the B-type material, and then once it crosses in the B-type material, it will recombine with one of the holes. So it will fill one of the holes in the valence band, and then it will disappear. It gives away its energy, and then it disappears. Okay? And as a result, when you have continuous flow of high energy electrons from here to here, this means that the energy level on this side will drop down. It will go down. While here, because you keep on adding electrons to this side, okay, and these electrons recombine with holes, the energy band or the energy levels on the B-type will go up. And this will continue until there is no overlap between the conduction region here and the conduction region here. And then the process of diffusion will stop. Okay? So this is one way of looking at it in terms of energy. High energy electrons can diffuse. They can move from here, from the conduction band in the N-type material, to become conduction electrons in the B-type material. But once they move to the conduction to the B-type material, they lose in energy. They drop back again into the valence band. They recombine with one of the holes. So they fill one of the holes in one of the impurities, and they lose away their energy. But the process of continuous losing of high energy electrons means that these energy levels will drop down. The energy levels on the N-type material will drop down. While here, because the B-type material is really losing also its holes, but it's gaining high energy electrons, its energy levels will go up until there is no overlap between the two regions. So after 1 microsecond maybe passed, this is how things look like in the BN junction. This is a conduction band in the N-type material, and you can see it does not have any overlap with the conduction band in the B-type material. It means a conduction electron here does not have enough energy to become a conduction electron here. It cannot cross anymore. and there is a barrier. There is a barrier that was created, and this is created by the very strong electric field. And for an electron to be able to cross from here to here, there must be some external force, external electric field that will push it, give it enough energy to be able to make the jump. And then once it makes the jump, we can have current flowing in this diode or in this PN junction. The voltage difference created here, as I explained, is 0.7 volts. The positive side is here, the negative side is here. Because here you have positive ions, here you have negative ions. The positive ions are inside the N-type material, the negative ions are inside the B-type material. So this is the state, this is how the energy levels looks after steady state. Depletion region, where there are no free charges. Electrons in the N-type material, they do not have enough energy to become conduction electrons in the B-type material. They simply cannot cross. They are waiting for some external force to give them a hand, give them enough energy so that they can they go through the depletion region and they break that barrier. And this exactly look like you have a battery, and this battery here is 0.7 volts. Okay, in order to have a current going in the opposite direction, and I will put here some resistance just to limit the current, you must put a battery which has a voltage of greater than 0.75. This has to be greater than 0.7. This one here, this V, has to be greater than 0.7. Actually, I'm drawing it in the wrong way here. When I want to say it's greater than 0.7, it has to be done this way. So this is 0.7, and this is V. V will have to be greater than 0.7. If this happens, then the electric field of this one will be able to push the electrons across this barrier, this 0.7 barrier. So it will push the electron this way, or it means it's flowing a current in the opposite direction. One interesting application of BN junctions is that BN junctions are used as solar cells, and there are lots of research being done here right now on solar cells, even in mechanical engineering and their applications, so on. But a solar cell is nothing really but a BN junction. So you have there an N region, you have a B region, you have a depletion region in between them. You have very strong electric field here. When you have some light shining over this cell, the light, as you already mentioned to you, you already know, it consists of packets of energy, and these packets of energy are called photons. So these photons, they allow some electrons, they give them enough energy, allow them to break from their atoms, and they leave behind a hole. So they create what we call an electron hole pair, and then these electrons will accumulate in one plate, creating a negative voltage relative to the other plate, which is the ground. And then you can start to have, if you have so many of these connected in parallel, you have a sufficient voltage source with enough power. And this is how we can get this behavior. So it's really photons, it's energy. It allows electrons to gain enough energy to break away from their atoms. They become conduction electrons, they leave behind holes, and then they create a voltage difference between the two electrodes of this battery. It's a very interesting application, and I advise you to read the application part at the end of chapter 1. It's fully dedicated to solar cells. Now we move to the interesting part. Why is diode or a BN junction is a very useful device? Now you'll get to understand why this is the case. This is a BN junction, and in reality, if you buy a small BN junction, it looks exactly like this, but on a much smaller scale. There is, of course, high power and high ampere diodes, and these are big devices. They are bulky, okay? But this one is a small one. Probably its length is about 0.5 centimeter. And its diameter here will be about maybe 3 millimeters or so. Anyway, so we have two ways of applying a voltage, external voltage to the diode. As we agreed, there is a potential barrier here. It's preventing electrons from moving from the N-type to the B-type material. They cannot cross. There is a very strong built-in electric field here. There are positive ions here, negative ions here, very strong electric field pointing from right to left. So it's trying to push electrons back from left to right. So it's trying to keep them inside the N-type material. There must be some external force to allow them to move. So the first bias condition we're going to study is called the B-type, it's called the forward biasing. Forward biasing means that you bring an external battery, you connect its positive side to the B-type material, you connect its negative side to the N-type material. What does this do is very interesting. This negative side can supply high. There are two ways of looking at it. For the first one is that this battery creates a very strong electric field. This electric field is pointing from, you can see here, this is, you have to connect this positive side. So the electric field is really moving from left to right. So it's actually trying to push electron from right to left. So it's trying to help the N-type electrons to cross. And if this bias voltage is greater than the 0.7, as I shown you in the previous circuit, these electrons will be able to cross the barrier and then become conduction electrons here, recombine with holes, and then they move from one hole to another, from one hole to another, and then you get a current, and then the circuit closes. This terminal will supply more negative electrons. These negative electrons cross the barrier, they go to the other side, they keep on jumping from one hole to another, and then they cross here. So there is a whole current going on here. This is what we call valence band current, and there is an electron current going here, which is conduction band current. One other way of looking at it is that when you connect the negative side here and the positive side here, this negative side can supply high energy electrons, causing a shift in the energy levels of this N-type material. So the energy levels will go up, while this positive side really will attract any electrons that exist here, creating even more holes, which means that the energy levels on this side will go down. So this one has energy levels going up, this has energy levels going down, and then there is again an intersection between the conduction band here and conduction band here, meaning that an electron with sufficient energy here can cross the barrier and then become a conduction electron in a B-type material. So this is the case I mentioned to you. When you connect the B-side material here to the positive side of a battery, and you connect the N-side material negative side of the battery, the energy levels of the N-type material will go up because the battery, the negative side, supplies high energy electrons. So these electrons, this one way of looking at it, they have more energy, everything is shifted up, while the positive side will really suck any existing electrons that you may have. So it's bringing down these energy levels, creating more holes, brings down these energy levels in the B-side material. So now you can see there is an intersection. If you try to roll this one, some electrons here have enough energy to cross to the B-side material and become also conduction electrons. So we have flow of electrons from the N side to the B side, and when these electrons cross, okay, they of course they can recombine, keep on jumping from one hole to another. So you have hole current happening here, you have electron current happening here, but the circuit is closed, and the electrons flow in this direction from the N-type material to the B-type material, which is equivalent to a positive current flowing from the B-type material to the N-type material. And I'll make a little bit of a jump here. The circuit symbol of a diode, it looks something like this. This is the anode, this is the B-type material, this is the cathode, this is the B-type. So this is this is the B-type, this is the N-type, this is the anode, this is the cathode. So you can see here what we have proven is that if you connect a sufficient voltage across this diode, what will happen is that current will flow in this direction. Current can flow in this direction, which means that electrons can diffuse from the cathode to the anode. This is what we have really proved. So in one direction, it can conduct current very well, and as a result of this external battery, the size of the depletion region becomes a little bit narrower. Okay, because you have more electrons, so these more electrons, they can really fill some of the positive ions here, and you have more holes, they can fill some of the negative ions here. So you still have the 0.7 barrier here, but the depletion region becomes a little bit smaller. And those of you who will go further in studying semiconductor physics we'll see the equations that prove that this is indeed the case. The depletion region becomes a little bit narrower. But just remember, you still have a barrier of 0.7 volts here, and the external source was able to overcome this barrier. Now we move to the second part, and this will prove to you that why this diode is very useful. We talk about the second type of biasing. It is reverse biasing of a diode. Reverse biasing means you connect to the positive, to the p-type material connected to the negative side of a battery, and you connect the n-type material to the positive side of the battery. Okay, look what will happen here. This positive side will attract high energy electrons away from the junction. So it's even making the energy levels here even go down. While this negative side will, we can say it will supply some electrons here to this side, meaning it will shift these energy levels up. So this is actually making it even more difficult for electrons to cross from here to here, and there will be no current. So under this condition, when you make this negative biasing, the high energy electrons that you have here are being sucked by this positive side, and the holes, we can look at it that way, they are being sucked by this negative side. So you can't have any conduction current flowing in this one, and this looks like open circuit. Actually, it's effectively open circuit, but most of the voltage of the bias circuit will appear across your depletion region. So the voltage across the depletion region will be significant. So this is one way of looking at it. One other way of looking at it is that this battery creates a very strong electric field. This electric field is pointing from the N side to the B side. You can see it's positive here, negative here. So this means that the external electric field is pointing this way. It's pointing from the N side to the B side. But this means it's trying to push electrons in the opposite direction. You can see it's trying to push electrons away from the depletion region. It's trying to stop them from diffusing, and you cannot get any current flow. This is why this device is very useful. It allows current to flow only in one direction when it's forward biased. But when it is reverse biased or negative biased, sometimes we call it negative biasing, it looks like an open circuit. You cannot have any current flowing in this one. And there are so many applications for that in creating, in receiving high frequency signals and rectification of AC signals and so on, as I will show you in the application part. So as I explained in the previous slide, the fact that the N-type material is now connected to the positive side of the battery means that the energy level of the N-type material will go down further. And the fact that the p-type material is connected to the negative side of the battery means that the energy levels of the p-type material will go even higher. And you can see the intersection between the two energy bands is it's even worse. So any electron here will be required to gain lots of energy in order to cross. It's even worse than the case when there is no external source being applied. And you can see the barrier is even higher here than 0.7 because it looks like an open circuit, and most of the voltage, most of the reverse voltage will be added to the potential barrier that you have here. So without any source, you have a 0.7 volts across this junction, but when you have an external source that adds more to that 0.7, then this barrier becomes worse. Okay, so now we have a situation where no current can flow, and it's known from semiconductor physics that because of this reverse biasing, because some electrons are being shifted away by this strong electric field, the depletion region becomes even wider. So that's why wider depletion region. The depletion region becomes even wider. So in forward biasing, the depletion region becomes smaller, and reverse biasing, the depletion region becomes even larger. Okay, so this is why this device is a very interesting device, and we have many applications for it.